before the start of this session, I know time is very short, I should like to tell you few things which probably you may think, or I am thinking, that what is the purpose of this particular workshop. Now first of all, I tell you what we are doing. It is definitely a teaching and learning process, but through discussion amongst the colleagues. I am teaching this subject for a long time at IIT Kharagpur and nurturing these subjects to my research. You are also teaching this subject at different institutes and colleges. So this you think as a discussion, sort of discussion, not as a direct instruction, because you all know this thing. But the main purpose is that there are two things. First thing is that why a person writes a book, person of some institute of higher learning, the basic purpose things are there already in other books, but still he writes a book. This is the main purpose, is that he tries to express things the way he has seen from his own experience, so that other can understand this better. That is his perception. And second is that by virtue of his exposure to a broader field, he feels that this should benchmark the standard of education. You understand that benchmarking of the standard of education. With these two only the person write the book. Now again, here also this discussion has got two effects. One is that we should again recapitulate our basic things, what we are teaching at our places, all of you. And at the same time, if you know the thing in a more depth and make it more clear, then it will be easier for us to transfer the knowledge. Always you see that if I have some knowledge level X, and if I transfer something of 0.6s to others, then that becomes fantastic. But if I transfer X to X, then it becomes very shallow. So that's why it is always imperative that a person which we feel at IIT very much, the person teaching a subject must know the subject in depth, through discussions, through participation with others in conferences. Why these are so much important? Why do we tell that research and teaching are coupled together? They are very much is a complementing one another. So that is the reason. Sometimes if any difficulty, any doubt, you don't feel shy to ask that why are you writing it, why are you, I don't mind that we don't have to cover a particular portion in this coordinator workshop that I have to tell all those things. Where there are doubts. For example, I tell you once, I remember, probably many of you know that I have launched many courses in the NPTEL program, National Program on Technology Enhanced Learning, like thermodynamics, one of my very lovable subjects. I love this very much. Then fluid mechanics also is there in YouTube. So one workshop of this type at IIT Madras, but much less number of teachers was conducted, and I categorically told their coordinator, Professor Mangal Sundar, that I like this coordinator's workshop to be conducted like that. I may not address all because of the constraint of time, but let one individual and like all ask some question that where he has some difficulty. So I will explain that. I remember one person called, sir, I could not understand the triple point very well. Can you explain the triple point from the phase diagram, PT diagram of a substance? Oh yes, fantastic. I did it. Then somebody told, sir, I could not understand the philosophy of Clausius-Clapeyron equation. Where from does it come? Just like that. Some steps, within these steps I have some doubt. Sir, why do you come from this step to finally derive the Clausius-Clapeyron equation? Well, fine, I did it. So this way if thing goes, I think when we are all here teaching fluid mechanics to different students across the country, so therefore it will be much better. So that's why I request you, all of you, to participate in this manner. It's not that something we are telling you and you are taking the notes and all these things. This is not the philosophy. Sincerely. So I want to address you that what are your problems, you tell me, I will understand. Sir, there are my difficulties. And at the same time, another thing, that when we are telling a bulk of the material, then we try to tell you two things. One is the total exposure and the standard of exposure, which should be used as a benchmarking slowly at different institutes depending upon the standard of the students. Obviously, this is another factor. All students cannot be of the same standard, but slowly this has to be taken up. And at the same time, we have to know that this, apart from the coverage, has depth also. that how much we will go. So if we clear the depth or the concept of the student to some extent, our concept has to be cleared much more than that so that we can tell it. So these two are the main reasons I feel personally teaching this subject for a long time. Dr. Joshi Haran is my friend, he knows we are together. So I feel from my personal perception that this is the philosophy of today's workshop. So today, after this, I will start something of fluid kinematics. Now, if we start the fluid kinematics, first of all, we have to know what the fluid kinematics means. So therefore, I write this word. This takes some time, but I write very fast, so unnecessarily. Now, kinematics word means that it deals with the motion. Kinematics, not fluid, solids also. Kinematics word means it deals with the motion without knowing the cause of the motion. Motion is caused by the force, but I don't want to know what is the force, but I describe the motion. If I run, somebody tracks my trajectory, my art of running, my speed of running, doesn't matter who causes me to run. So therefore, leaving behind the causes, that is without analyzing the force in any system, analyzing its types of motion, because it is very important in describing the equation of motion. So that is the kinematics. That means we study its motion. And the kinematics, therefore, very much involved for fluid flow, if there is a continuous motion, is the velocity. And it is the consequence of this kinematics, as we have seen in the very first lecture, that since the fluid deforms continuously, therefore this kinematics, that means the fluid motion, is responsible for its deformation. Linear deformation or angular deformation, that means the shape changes. Deformation means the shape changes. So say change of shape and deformation is responsible for kinematics. So therefore, kinematics first part is the description of the fluid motion, and second part is from that description, how do you finally relate the deformation, that is the change of shape of the fluid, with the motion. Motion means the continuous change of motion, that means the velocity. Okay, so with this in backdrop, let us see that there are two approaches in describing the fluid kinematics. Now, two approaches, first of all I write, one is Lagrangian approach. This all you know. So therefore, Lagrangian approach, another is Eulerian approach. Another is Eulerian approach. Now, fluid composed of particles, we already told. Now, usually by kinematics, very first understanding of us is that in a fluid medium, flowing medium, we want to know the flow field. That means if there is a flowing fluid in a certain domain, we want to know what is the velocity distribution. That means velocity as a function of space coordinates at different instants of time. This is basically, we want that we must know these things. Now to know these things, there are two approaches. One is Lagrangian approach, another is Eulerian approach. Now, in Lagrangian approach, what is made is, what is this? In Lagrangian approach, now again I write, Lagrangian approach, what is done, the behavior of each and individual fluid particles constitute the fluid flow, because a fluid medium, flowing medium, constituted by the particles. So Lagrangian approach is what? Now, for example, if I tell that this is the velocity distribution at particular instant in the flow field, from another angle, from another point of view, one can tell, since the flow is composed of several particles, so this is the velocity distribution of the particles at that point at that time. For example, I tell this is the velocity at this point, space, one point, at a particular instant of time. That means that is the velocity of the particle which is existing at that point of time at that location. So therefore, from particle point of view, understand, the particle point of view, it is the velocity of the particle. So therefore, Lagrangian approach, the particle point of view, the Lagrangian approach takes the particle point of view. That means each and every particle constituting the flow is being tracked, and its trajectory is found, from which we derive the velocity and acceleration information. That means it basically derives the information of each and every particle constituting the flow, and thus we can find out the total kinematic information of the flow field. So therefore, Lagrangian approach is simply designated like this for a given particle. That means when we track the particles, particle has to be given some identity. How do you differentiate one particle from other? So particle identity is given like this. For example, this is the position vector of a particle. This is mathematically expressed as that is a function of particle identity. Now particle identity is given by its initial position. If I start, that means if I make some time, reference time at t is equal to t0 start, that means start of observation, that means initial time. So at initial time, when I start, this is the initial time, different particles at different positions. So the initial positions of the particle describe its identity. Otherwise, there is no other way out to find out the particle identity. So each and every particle is identified by its own identity, by its position at the initial time. So therefore, the initial position vector is the particle identity. So at any time instant t, the position vector of a particle depends upon its identity, means its initial position and the time. So this is precisely the Lagrangian approach. Now you can split it in terms of, for example, rectangular Cartesian coordinates, that S, this I am not, actually this takes time, ux, j, y, k, these are unit vector, so that so that we can write x is a function of x0, y0, z0. Similarly, the initial position can be written at x0. That means if I change it to the components, that means the displacement component, so this will be a function of all, t, z0 t. So z is equal to a function of, this is actually z0 t. Now therefore, this is the first step of the Lagrangian approach. So the velocity v is the derivative of this, that means this is ds dt, and this becomes a function of s, some function of this. Similarly, we can write u v w. What? V is defined as I, these are the unit vectors, j v plus k w. So this is simply, so this will be some function of x0, y0, z0 t. That means we define, similarly we define acceleration vector A as d square s dt square. And similarly, this is also some function of s0 and t. That means the position, the velocity and the acceleration of each and individual particle at different time is plotted. Time is inherent in it. As I move, as a particle moves, the time is inherent in its movement. That means along with its movement, its entire kinematic history is plotted, and this is plotted for innumerable particles constituting the flow. Therefore, you see the Lagrangian approach possesses a huge task which are difficult to handle. So therefore, we go to the most easier method, is known as Eulerian method, as proposed by Euler. Lagrangian method was proposed by a scientist. They are great scientists, Lagrange, you all know. And Eulerian method is proposed by the great man Euler, Leonhard Euler. So Eulerian approach is rather, if you see, is much easier. What Eulerian approach tells, that we don't bother about the particles. We consider a continuum, which I explained yesterday, that matter continuous distribution of molecules and similarly continuous distribution of the particles, moving particles, macroscopic particles. I don't want to know the particles. Rather, I fix the velocity, I ascribe the velocity at different spatial locations, which may change with time. And at particular instant, velocity at a particular, I only understand velocity at this location, given by space coordinates. So this will be definitely velocity of a particle which exists at that location at that time, but I don't bother who is there. But I can tell that this is the velocity. So today if somebody measured the sound intensity in this room, so he will tell at 9:45 this is the sound intensity at Kalidas Auditorium. But doesn't bother whether the sound is being delivered by Professor Shom or somebody else. So I want to describe the spatial variation of the velocity at different instant of time. That means velocity as a function of time, and automatically it will take care of the particle, that the particle which exists at that time. So Eulerian method actually describes velocity as a function of space coordinate and time. There is no identity of the particle, there is no particle business. That means it simply defines the velocity field. This is known as velocity field. That velocity is a function of space coordinates and time. So if you decompose, u is a function of x, y, z and t. Different component of velocity, v is a function of x, y, z and t, and w is a function of x, y, z and t. Now from here you can go to Lagrangian approach. You can convert, and accordingly the acceleration vector is defined as. So therefore here it is very easy that we don't bother about number of particles. So velocity is expressed as a function of space coordinate and time. At a given instant of time, at a given location given by space coordinate, the position vector, the velocity is this, and this is the velocity of the particle that arrives at that point. Okay, so this is much easier. Now from here you think that we can go to Lagrangian approach. Eulerian to how you can transfer one into another. Lagrangian approach. From Lagrangian approach by differentiation, we can go to Eulerian approach. Similarly, by Eulerian approach, how we can do that? dv is ds dt. So if u, this is a function of s bar t. Now if we integrate this with time, I am doing little first the mathematical part. If you integrate this, because concept is more important, mathematics is a tool. If you have any problem, you tell me. If you integrate this, we will be able to generate s bar as a function of t. And if we put the initial condition at t is equal to t0, this is because when you integrate this indefinite integral, you include a integration constant. So to make an explicit function, we have to find out the integration constant in terms of the problem variables, for which we require boundary condition or initial condition. This is the integration with respect to time, we require initial condition. This initial condition is nothing but, is nothing but 0, is your that means this initial condition takes the Lagrangian approach. That means this is the Lagrangian approach. Therefore, with this initial condition, integration of this is possible through some mathematical steps which tells s bar is a function of s0 bar t. That means one can go from Eulerian approach to Lagrangian approach, and also from Lagrangian approach to Eulerian approach. But this is the approach which is much convenient and is being followed for the analysis of fluid mechanics, and which we will be following. Clear? Let me now very quickly see a problem, so that things will be much more clear with this definition. Then I will ask that if there is any other problem. Now this is a one-dimensional flow field where this is the description by Eulerian method, that u as a function of x and t. Let us consider one very simple problem to clear our concept, that let the velocity is given as a function of time and function of x and t by this simple expression x plus t. So now our purpose is to find out the Lagrangian description of the flow field. A general Lagrangian description of the flow field, that is the problem. Determine the displacement of fluid particle whose initial is x0, initial displacement, initial position is x0 at initial time t0 in the Lagrangian system. Language is not very important, you have to understand the problem. So u is dx dt, I told that. Now you are integrating. Now this integration gives this, that you know dx dt minus x. That is a very simple thing that is done in the first year is t. So the complementary function tells that it is a exponential function dx dt. It is first order linear equation. So a e to the power t, a is the integration constant, and if I make the particular integral d minus 1, d is the operator, d is d dx, d dt, sorry, here d dt. So if you operate this with t, you get minus t minus 1, because t into minus 1 minus d to the power minus 1. You know this thing. This is a simple first year mathematics. Okay. So there is nothing, only mathematics. Where the fluid mechanics come, you see. Now the constant A is found from the condition that at t is x0 at t is equal to t0. So constant coming, first year mathematics, substituting this. So here, this initial condition, imposing this initial condition at t is equal to this, tags the Lagrangian concept. And finally, we get x as a function of x0 and t. Mathematically, it is what? X as a function of x0 t. Because we put the initial condition, find out the integration constant and put that. And this is nothing but the description of the Lagrangian version. That means the trajectory of a particle whose identity is given by x0. That means his initial location is x0. This will make a trajectory like this. By putting different values of time, we get the different location. So we can put the trajectory. There the time is inherent with its motion. Clear? So therefore, Eulerian approach is that I stand, for example, there is a stream of persons coming. I want to see everybody. There are two approaches. I still stand and I see the persons crossing me. And another approach is that I go with each and every person to see what he is doing, where he is going. That's the difference between Eulerian and Lagrangian approach. Okay. Another problem I solved, that is the Eulerian to Lagrangian to Eulerian approach. It is other way, that this is the Lagrangian version. It is a two-dimensional flow. Now we have to express x as a function of t and y, not x, u as a function of x, y and t, and v as a function of x, y and t. You just have to formulate that. If we have to find out the Eulerian version from this Lagrangian version, the problem is that in Lagrangian system, hey, you don't disturb me. So if it doesn't come, then I can help. It is not better to teach. If it doesn't come, if it gives this much amount of problem, you please check it. It's coming. Why it is doing like that? Oh, hatta pure jache. Oh, they tell me I will not put that. Okay, I will not go there. Okay, fine, fantastic. It's my problem. Okay. So this is the Lagrangian description. So Eulerian description means I have to find out uv as a function of x, y, t. There should not be any x0, y0 business. That you have to understand. So now it is a mathematical trick. You find out u dx dt and you tactfully eliminate x0, y0. Here y0 is taken from here. X0, here x0 is substituted in terms of x. And y0 is substituted in terms of y. So therefore, everything is mathematical jugglery, first year mathematics. So concept is that you have to find out u as a function of x, y, t. That means velocity as a function of space coordinates and time. V as a function of x, y and t. That is space coordinates and time. So therefore, x0, y0 business will not be there. That means we translate this problem into mathematics, that we find out the derivative dx dt, dy dt and eliminate x0, y0 in terms of x, y. You understand? X variable space coordinates x, y. That is simply the thing. So therefore, if you just do this, then mathematically just elimination of x0, y0 you get from Lagrangian to Eulerian approach. Okay? It is clear or not? It's clear. This is given in my book. There is nothing new to just write down. But you have to tell the tricks, that where is the concept of the physical science, where does it link, and then what are the mathematics to be done. Mathematics to be done, you have to be skill, you have to have the skill of doing mathematics, elimination, this, that, but what is the concept of the physical science doing with that mathematics. Okay. Now next I go Next is acceleration. Now I tell that how to define acceleration of a particle. Let us consider that this Eulerian approach concept of acceleration. Concept of acceleration. Now we know that is a function of now with respect to a Cartesian frame of reference, we write that function of x, y, z and t, and w is a function of. Now defining acceleration in Cartesian coordinate system. Now let us consider it is the change of velocity with respect to time. Let us consider after a time interval of delta t, a particle has a displacement x is equal to x plus delta x, y is equal to y plus delta y, and z is equal to z plus delta z. Then because of this, consider delta t to be infinite small, which causes infinite small displacement in the particle. That means s is s bar plus delta s bar in vector notation. Now for this, let us consider u component of velocity, that u is changed from u plus delta u. This is makes a infinite small change in the x component of velocity. Let us consider. So this will be the same function of, only the arguments will change by the respective values, y plus delta y, z plus delta z, and t plus delta t. Well, now this can be written by a Taylor series expansion as del u del x, first the function u plus u is this containing these arguments plus del u del x plus del u del y delta y plus, this is very simple, del u del z delta z plus del u del t delta t plus higher order terms of delta x, delta y, delta z. This is an infinite series. That means second derivative delta x squared, delta y squared, delta z squared, delta t squared will come. So that we write higher order terms of all these small quantities, delta x, delta y, delta z, delta t, and these are very small quantities. I don't write that quantity. So just write higher order terms of this. So this we can write like this. Now, therefore, the change in the quantity delta u now becomes, if you see that, I will make it now. Can you see that? Yes. Therefore, this is okay. Okay. Now, therefore, delta u is del u del x delta x plus del u del y, again I am writing delta y plus del u del z delta z plus del u del t delta t plus higher orders of delta x, delta y, delta z, delta t. Okay. Now, if, here I am writing, here if now I write what is delta x, u is delta t. Delta t is so small that the displacement delta x can be written as u into delta t. Similarly, displacement delta y can be written as v into delta t, and delta z can be written as w into delta t. Because these are small, what happened? These are small displacement, infinite small displacement for infinite small time. If you now put this and divide entire thing by delta t, then you will get del u delta u by delta t as then del x delta t. What is del x delta t? Now I am not writing this. Del x delta t plus del u del y. Oh, sorry, u delta t. I am sorry, del x delta t. No, sorry, u delta t. So it is u del x plus v, because del x is u delta t and I am dividing by this. So w del u del z, because del z is w delta t, I am taking plus del u delta t plus, now this is higher order terms of delta t, that means this is written this way, delta t square and so on, because delta x is u delta t, y delta t. Higher order terms of delta x means delta t square, that means it is delta x square, this is delta y square. Higher order terms means delta x, delta y is here, it is square term, that means it is delta t square. And when you divide it by delta t, this term will contain delta t square. Okay, so this will contain term of delta t square. Now, delta t square means delta t whole square and delta t whole cube, like that. Now, if you take limit, if you have got any query here in the mathematics, you tell me, then you get that this limit del u del t is defined as acceleration. This becomes u del x plus v. This remains as it is because we have defined this as u delta t. So already we have considered the limiting value. What changes is there? That there is no approximation. This becomes 0, identically 0, because limit delta t tends to 0. All terms containing delta t and higher order of delta t becomes 0. So therefore, when you define this as acceleration as the limit, this is the x component of acceleration, we get this term. This can be written as del u del t plus u del x plus v del u del y plus w del u del z. I rearrange these. Clear? Now, what these things are, let us understand. So therefore, so far what we have done, from the definition of acceleration in x direction, ax, I have used the Taylor series expansion to derive ax, that in terms of the change of u with respect to here. Now we can write that this thing, that u is a function of x, y, z and time, and ax, which is equal to du dt, this is du dt, ax, del u del t, delta t tends to 0. This is written as du dt, that is rate of change of u with time, consists of all these things. Del u del t, again I am writing del u del t plus u del u del x plus v del u del y plus w del u del z. What is this? You know, all of you know these things. Now you see, this represents mathematically the change of u with time at a given location is a partial differential. That means x, y, z constant. That means that any location, what is the change with respect to time. And these things are associated with the derivatives of u with x, y, z. And these things are associated with the change of velocity with spatial location. You understand? Change of velocity with spatial location. So this is known as temporal derivative. That means the value, the parameter changes with time at a given location. When the parameter is the velocity, then it is the change of velocity with time at a given location, which is the temporal acceleration. And this is known as convective derivative. That means the derivative is with respect to the spatial condition, derivative. And when this is velocity, associated with velocity, then this is convective acceleration. And this is known as substantial or material derivative, which is known as, now in this case, is the substantive or material acceleration in x direction. So therefore, what most important thing is that when we want to find a change of certain quantity, as it flows in a medium, change of the quantity with time is inherent with the change with time from location to location. At the same time, the change takes place with the location. Two superimposition gives the change of that parameter with time. So therefore, the substantial acceleration or the total acceleration or the material acceleration, here derivative means derivative of velocity, that means acceleration, is sum of the temporal acceleration plus convective acceleration. And this can be written for all other velocities, that ax is del u del t plus u del u del x plus v del u del y plus w del u del z, and similarly ay will be del v del t, that is temporal acceleration, and this is the convective acceleration in y component. That means this is the change of v associated with the space del w del z, and this is az del w del t plus u del w del x plus v del w del y. This will follow accordingly, plus w del w del z. The similar way this can be proved as it was proved for this. Clear? That means acceleration is composed of temporal acceleration parts and the convective acceleration part. So change is depending on that. A very good example which I usually give to my students, that you can also use, that it is a seeing a particular phenomena how it is changing. Sometimes I tell like that a person coming from Howrah, Calcutta to Kharagpur. Now you see that if he travels, you see that it is raining at Calcutta, but he comes with a car where he cannot see anything, everything is closed. But when he gets down at Kharagpur, he sees that there is no rain. Then what is his conclusion? That there was no rain at Kharagpur, it is only at Calcutta. It may not so happen, because he may not know that whether the Calcutta still it is raining or not. It may so happen that when he started from Calcutta, that time Kharagpur was also raining. And if he makes a telephone call to Calcutta, he will find out that Calcutta also rain has stopped. That means it's a temporal phenomena. That means the change which he is seeing from coming from Calcutta to Kharagpur, it is not because of the distance Calcutta to Kharagpur. It is the change in the temporal change with time for any given location. That time Kharagpur was raining, Calcutta was raining. Now everything is stopped. It may happen due to that. Or if he finds from the telephone call that no, Calcutta it is still raining, and a person at Kharagpur says, no, it was never raining at Kharagpur, bhai. From early morning we know it is never raining. That means it is because of the change with the space. That means it is raining heavily at Calcutta. The rain slowly stopped as it comes to Kharagpur. That means a distribution is there in the space, and also that changes with time. So therefore a temporal change and the change, convective change because of the locations, both together makes a change. That's why sometimes we tell what is acceleration. Acceleration means that it changes. Sometimes the flow is steady. When the change does not take place with time at any location, that means temporal derivative is zero, then the flow is known as steady. Now I define in this context what is a steady flow. That means if velocity and acceleration is not a function of time, then flow is, sorry, yes, the flow is known as steady. The flow is known as steady. That function of only space coordinates, the position vector. That means that it is the steady flow. So therefore, these terms are 0. So there the acceleration is only because of the convective change. But at any instant, the velocity doesn't change. When the flow takes place through a nozzle, we tell that acceleration is there of a fluid particle as it flows through the nozzle. You know that thing. For the continuity, the area is changing. But at any cross section, for example, at the discharge, you see velocity is not changing, right? I am seeing that velocity at the exit remains constant throughout. Why are you telling there is an acceleration? There is an acceleration because of the convective acceleration. If you find out the velocity at the inlet, you will be see it is drastically less than that at the outlet. That means here the acceleration takes place because of the convective acceleration. That velocity changes with space coordinate. But on the other hand, if you see that a flow is told to be non-uniform, that means, uniform, that means when this velocity is only a function of time. So acceleration is only a function of time. It doesn't become a function of s. That means the flow is uniform. Flow is, velocity and accelerations are uniform, are same at all locations, but they may change with time. They may change with time. That you flow through a constant area duct. If you don't consider its variation across the section, in case of turbulent flow, across the section variations are negligible except near the wall. But there what happens, if you go on changing the flow rate, then what happens? The velocity, though same at each and every cross section, but their value will go on changing at each and every cross section with time. So therefore, the flow may be steady or unsteady depending upon whether any flow parameter, steady flow means any flow parameter is independent with time, unsteady if it is not independent with time. Similarly, uniform flow means the velocity and accelerations are independent of the space coordinates, and non-uniform flow means they are not so. So out of these four, any two combinations can come. Most general thing is that unsteady non-uniform, and steady uniform is another extreme. Nothing changes with time, nothing changes with space. Total things are uniform. So therefore, in that case, temporal 0, convective 0. That means there is absolutely no acceleration. So acceleration will be caused both by unsteadiness and both by non-uniformity. Clear? This is the concept of acceleration. What is temporal acceleration, what is convective acceleration, and what is total acceleration, sum of this, material acceleration or substantial acceleration. And that is called as acceleration. When we tell acceleration, it is substantial or material acceleration. Clear? Okay. Thank you. Any question you can ask me before I go to different other aspect of the fluid mechanics, of the kinematics. Now here, I told you at the beginning that kinematics first define, of course, the streamlines, straight lines are there, but time will not be there. Okay, now I define that three things. Streamline, everything is difficult. There are three lines defined in fluid mechanics. What are those things? Streamline is defined, it is a consequence of Eulerian approach. That means that any instant of time, if you can draw an imaginary line in a flow field, so that at that instant the slope of that line, that means tangent at any point to the line, is the direction of the velocity vector at that point. And there may be number of such streamlines. That means if you have any streamline at any point, and if you at any point if you find out the slope direction, that means tangent, if you draw the tangent, this will represent the velocity vector. And this is at a particular instant, t, at a given, t is given. That means A streamline, number of streamlines, a map of streamlines has to be specified by that instant, because for an unsteady flow this is changing. For a steady flow, this map will remain invariant with time. So this is the definition of streamline, which comes as a version of Eulerian approach. And one interesting thing comes from the common sense that two streamlines can never intersect each other. Why? Because if you tell that this is my streamlines, series of streamlines at instant t is equal to t1, then I will find that at this point there are two tangents, one for this streamline, another for this streamline, because these two are intersecting. So at any point, a fluid cannot have two velocities, because directions are changing, means different velocities. So there is only one velocity, one particle and one velocity. So therefore, since at any point there cannot be two velocities, so therefore the streamline at any instant cannot intersect each other. Path line is what? Path line is a consequence of Lagrangian version. It is simply the locus of the particle of a given identity. Identity is fixed by what? At the initial time, the start of our investigation, different particles at different positions. So by their initial positions, identity is fixed. So for a given identity particle, what is the locus of it? That is the path line. So in a path line, so that means you have to, what is the specification? Streamlines T given, path line X S0 given. That means it is for the particle S0. S0 means which is identified particle, this identity, which has S0 at T is equal to T0. That means a path line has to be prescribed or specified by the particle identity. And therefore, if we go along the path line, time is there inherent. That means move from this point to this point, I require some time. But here, if we want to move along streamlines, though physically we don't move, but if we trace my pen along this streamline, it is at the same instant. There is no change in the time. You understand? But here, there is a change in the time in the path line, because path line follows the trajectory or locus of that particle. So therefore, a path line can intersect, a simple path line can intersect the own path. That means for a single particle, that if it intersects, it means what? That initially, if this point, while you trace this path line, was at some time, so the velocity was in this direction. But after some point, after some time, this particle can come again at the same point with the different velocity. That depends upon the flow field. The particle can come back and can take the other velocity even at the same point. Similarly, two path lines may intersect. Why? This is because you can tell, sir, path line also shows the slope, also shows the velocity. I understand. dx dt is the velocity or ds dt. But this is for one particle, this is for another particle. And this point, intersection point, does not show that they are at the same time. Because this is a particle trajectory. When this particle comes to this point, the time instant, and another particle coming to this point, time instant is different. So therefore, it is a consequence of all these concepts that streamlines cannot intersect each other, but path lines can intersect. Okay? Now here, another thing I tell you, that equation of streamline, equation of path line is the Lagrangian version. That the Lagrangian equation of motion, or Lagrangian equation of kinematics, not motion, kinematics is the equation of path line. But equation of streamline, how you will make the equation of streamline? Very simple. Property of streamline is that at any point, velocity vector is tangent to the streamline. That means, if I consider simply a small element ds length along this streamline, along the curve of the streamline, then we can write that by the definition, this is 0. Because this is tangent to this. So the cross product is 0. So this cross product is 0 means what? I can write what is ds? V is I u if in terms of the velocity component. These are very simple, and ds is I dx plus so if I write this I j k u v w and dx dy dz. In terms of determinant, this is simple mathematics. One can find that dx by u is dy by v is dz by w. And for a two-dimensional case, you simply get dy dx in a two-dimensional plane v by u. This is very simple to understand, that in a two-dimensional plane, xy plane, for example here, if I have xy plane, a streamline is there, y as a function of x, then dy dx at any point must be is the direction of the velocity, that must be the ratio of the y component of velocity to the x component of velocity, because the resultant velocity makes an angle to the x-axis, which is given by its y component by x component. So this is very easy to understand from school level knowledge. So this comes. So this is the definition of streamline in space. Okay. Now most important thing is the straight line. So what is straight line? Straight line's definition is that, so I think streamline and path line concept is clear to you, that what is the difference between streamline and path line. Streamline is a consequence of Eulerian version. At any instant of time, series of lines, so that tangent at any point to any of the lines gives the velocity vector at that point, whereas path line is simply the Lagrangian version of kinematics. That means it gives a series of curves which are nothing but series of locus of all the particles of different identity. And in the locus or the trajectory, or that is called path line, time is inherent in it. Now, what is straight line then? Straight line is very important. Straight line is the line, is just definition is that is the locus of all particles which passes through a fixed point. Which passes through a fixed point. Locus, not locus of all particles, I am telling locus of the final position of the all particles which have passed through a fixed point. Try to understand one thing. Locus of the path of all particles which have crossed through a fixed point. That happens in our experimental flow visualization. Flow visualization, what we do, we put dye in a particular point, and fluid particles crosses that particular, when crosses that particular point, all fluid particles may not cross that point. That is true. But the number of fluid particles which crosses that point at a given instant of time reach some other locations in the flow, then if we join that location, the locus of that location, final location, gives this straight line at that instant. Straight line at that instant. So straight line is specified with the instant of time. So at a given instant, the straight line is the locus of the final position of all the particles that have crossed a particular fixed point. That means to define a straight line, you have to define a fixed point through which all the particles have passed, and also at a given instant. So if this be in your mind, so a straight line concept can be made like that. Let us consider this is a fixed point P. And let us consider an unsteady flow field. An unsteady flow field, what happens? Now let us consider, I consider my time t is equal to t0 here, starting time. T is equal to t0. And I like to specify the straight line at t is equal to t1. That means a time which is between t to t1, several times will be there, which is denoted as t. The number of instants will be there from t0 to t1. t0 is the starting time. At some other time, t0 plus some other time, that t0 is just now after 1 minute. t1 is 1 minute from now. So therefore, within that duration, t0 minus t1, number of particles have crossed through P. Now let us find that at t is equal to t0, the particle which crosses goes via this line, trajectory. And at time t1, it reaches here. It reaches here. Okay. Then another particle that comes here at some time greater than t0 but less than t1, some other subsequent time, has gone by this path. This path is changed. This path. Because of the unsteadiness, this velocity is changing here, the direction is changing for each and every point. So this particle is not guided by this. That is the thing, by its earlier particle. This will be guided by another line because everything is changing with time. So at t1, this particle reaches here. Let us consider another particle which has crossed this point for some other time which is after this time, but within this duration. And this particle cross this like this. This particle follows this like this and goes here at t is equal to t1. So the particles which have crossed this from initial point, 3 particles I take, they follow the different trajectories. Because why? Because path lines are changing, because the velocities are changing at each and every point with time, unsteady flow. And now, if I join this path, I get a straight line. And straight line always joins this point, because always there is a particle at this point at any instant of time, t1. So at t1, this is the locus of the feet of all the particles that have crossed at different times, starting from the initial time and subsequent time through this point, but followed the different trajectories, and they come at different points. So if we join, this is the straight line, which is the locus of the final location, that is feet of their trajectory at t is equal to t1. Now consider if the flow could have been steady, everything is same with respect to time. That means the second particle, the red one, he will follow the same line and he will stop somewhere here. And the another particle, he will also follow the same line. It is a steady state that I follow, my father followed my grandfather, I follow my father, like that. I will not do anything else except what they have done, because everything is specified. So each and every point, the velocity vector is specified. That means the path line of all identified particles and the straight line all coincide, and virtually this becomes the streamline also. So therefore at steady state, streamline, straight line and path line all coincide. But if the flow is unsteady, the velocity vector at each and every location go on changing time, the path line, streamline and straight lines are different, and they bear the respective identity. Clear? Hello?
Excuse me, sir.
Clear?
Hello, sir. One doubt, sir.
Please.
When time t equal to
Go,
0,
go. Yes.
all the particles will not lie on the same position.
No, we will not go to the same position. At t is, look, at t0, at t is equal to t0.
Yes, sir.
For example, this is the starting point. There are different particles at different positions. That is their initial identity. Okay, that is their identity. Some particle is there at this point also. Now we are interested, after some time from t0 up to t1, what are the particles which will pass through this point? You understand? Particles of different identities. That means the particle may have got some other location at t is equal to t0, but ultimately because of the flow field, at some time they have passed through this point. That time is t. Another particle may come here, another identity particle which at different position at t is equal to t0, but will pass through this point because of the flow field. So I am counting only those particles which have crossed. I have told that. All particles will not cross. You have understood? All particles will not cross or will not pass through that point. Okay?
Thank you.
The straight lines. No, two straight lines. How can you do that? This is the one straight lines at a given instant. So if you fix another point as the fixed point, and you tell that the same instant the two straight lines if intersects at this point, that can happen because this is another particle which can come. But if it is at the same instant that they cannot intersect each other, how they can intersect? Because at the same instant the position, this is the velocity of the particle. Velocity of the particle at that instant. So therefore, two straight lines, if you consider the another straight line passing through another point P, at the same instant t1, then this will be the locus of the particle which has crossed through this and has come to that t1. And this is the locus of the particle which has crossed through this P at this point. That means two particles cannot occupy that particular position at a given time, two positions at a given time. Try to understand that at a given time, if you tell that two straight lines intersect means what? Means that there will be two particles of different identity. Two particles of different identity, this particle and this particle. Their final position will be same at that T1, that cannot happen. Okay?
Sir, excuse me.
Please.
I have one doubt to ask, sir.
Please.
When you go back to the point of concept of acceleration.
Why? Who is the person?
Yeah, I'm here, sir.
Where?
Yeah, here, sir. Yeah, when you go back to the slide which tells something about.
Just raise your hand. Yes, please tell.
Yeah, when you go back to the concept of acceleration, on what basis you told that x is equal to x plus delta x?
What? H is equal to which one?
Yeah,
Please,
x is equal to x
this
plus
one.
delta x. Yeah.
This one? No. Which one? Oh, at that time you could have asked me.
No, we do not want to.
Yes,
point.
please, here.
Yeah.
Here.
Can you please tell me how to make us to understand to the students that on
I
what
don't
basis
understand. Which one you tell?
x is equal to, I think.
U into delta t.
No, sir. No. Previous slide, sir.
Previous slide.
Yeah. It is under
This
the concept
one.
of acceleration.
This one? Or this one? This one?
Yes.
This one?
Yes, sir.
Please tell.
Yeah. What is the basis on which you told that x is equal to x plus delta x and y is equal to y plus delta y?
What is the basis means? I assume that after a time delta t, any particle as displaced by its displacement is x from x plus delta x, the new position x. Oh, God.
That
This
is what,
the
yeah,
new
exactly.
position. This is not that delta x becomes 0. Don't equate like that. Don't read it like that. The new position
Yes,
x
sir.
is x plus delta x. That means this new position, chhod do.
Yeah, it is after some time interval x is equal to x plus delta
Okay,
x.
new x coordinate.
Now it is clear, sir.
Oh God. Please, that you have to understand that it is not a is equal to a plus d, a cancel. That means it is replaced by x plus d.
Thank you,
delta
sir.
x. Okay?
Thank you. Yes, sir.
Okay, thank you. Now I am happy. Okay.
Sir?
So,
Sir?
Sir?
Doubt.
yes.
What is the significance of streamline, sir?
Please. Straight lines. Straight lines, I told that is the basic application is that the flow visualization which we see, the lines, these are straight lines. These are not streamlines or path lines, but steady flow, virtually they coincide. When you inject dye at some point and we see the dye thread appears, that is nothing but the locus of the foot of the point particles which have crossed and taken the dye in the fluid flow. So the lines which we see by the colored dye injection, we see the flow visualization, the colored thread, that is nothing but the straight line. Because dye is injected at a particular point, it is not possible for any experiment to track a particular particle of some identity. That is for conception. But what happens is that usually we study the steady flows, and steady flows there I told there is no difference between a path line and a straight line. Because a particle at all instant when crossed through a point, they follow the same trajectory. And when he goes to the next incremental point, the same trajectory. So virtually what happened, ultimately the entire trajectory is fixed by his predecessor. Okay?
Sir, excuse me, sir.
Sir?
Sir, excuse me. Sir, is any situation is there like path lines and streamlines appears to be same?
Huh?
Any situation will be there, sir, like streamlines and path lines appears to be same, will
That
be
is for
happen.
steady flow. I am telling again and again. That is for steady flow.
Only
When the
steady
flow is
flows it
steady.
happens, sir.
When the flow is steady, when the flow will be steady, when all boundary conditions are steady, everything will be steady. A physical problem will be steady. When its boundary is steady, the inlet and outlets are steady, so ultimately the flow field will be steady. After a transience, the flow field will come to a steady value. When the flow is steady. But I think that we will entertain the questions afterwards, otherwise I will not be able to complete the rest part. Or better, I think that the deformation and all these things be stopped. Because if we interact, okay, I am happy to interact with this, okay, please tell.
Okay.
I think that is much better than covering
Sir?
more things. Please.
Can we use Eulerian approach for strict lines?
Huh?
Eulerian approach for strict lines.
I could not follow.
Can we use Eulerian approach for strict lines?
Streamline is a consequence of Eulerian approach.
Strict lines.
Straight line is a consequence of both Eulerian approach and the Lagrangian approach.
In
You
straight line-
understand the straight line, basically straight line is a consequence of Lagrangian approach, not the Eulerian approach. But why I am calling this? Because this makes a particular point fixed in the flow field with reference to a fixed point. Understand? But basically it is a consequence of, you can tell path line is a direct consequence of Lagrangian approach. But straight line is a mix of that. That way you can think Eulerian and Lagrangian concept. But when steady state is there, all three are merged. Okay? If you understand the basic definition and concept, then all these things, all the corollaries, you will be able to understand by yourself.
Sir.
Okay?
Sir, along a string line, velocity is constant or it may vary?
Along the streamline, velocity will vary. If the velocity varies with space coordinates, the flow is non-uniform.
No,
What is a
actually
streamline?
you have shown V in along a
V
string.
means that is the variable velocity. Whenever I tell V means variable velocity, T means variable time. So
No,
X means
sir,
variable.
while we saw the streamline
Okay, I tell you.
in a cylinder, over a
Okay,
cylinder.
I tell you again. Now problem is that I told that is that's why the coverage should not be more. Let us have a streamline like this. At any instant t is equal to t1. At this point at t1, this is the direction of the velocity vector and this magnitude is v. At this point, okay, this is given by some space coordinate. At this point s1, the velocity is v1. Magnitude is changing, that the velocity v is magnitude is v1 and direction is also changing. Everything can change. It shows only the direction, it doesn't show about the magnitude. That means from this point to this point there may be a change in velocity, both by magnitude and direction. And it may happen that magnitude and direction, everything. If nothing changes, then streamlines will be like this, parallel, the lines that the slope is same. Or line like this, the slope is same. Line like this, that means linear, that means slope is same. That means the direction is same. I cannot say that velocity will not change, velocity by magnitude may change. By concept, flow velocity may change from point to point. I told you, a non-uniform, unsteady or steady flow, whatever may be there, the velocity will change with space coordinate. So at any instant of time, the velocity will change with space coordinate. So therefore, the streamline at each and every point, the slope changes means direction change. I don't know about the magnitude. From streamline, change in velocity magnitude is not clear, but change in the direction of velocity is clear. Okay?
Sir, please. Sir, can you give some practical example for streamlines? Practical example, few practical examples for streamlines.
What?
Practical example for streamlines, where such streamlines can occur practically.
Streamlines are example means steady flow analysis. The streamlines are the path lines, the trajectories of the fluid particles from streamlines. Okay, streamlines are very important to find out, but in a flow field, if we know this series of streamlines, for example, a flow field at steady state or unsteady state at any instant t is equal to t1. It gives very useful information. Where it is applied means you will have to find the streamline. It is applying everywhere. If you do the research, that means you have to, the streamlines gives the information for what? What is the information? That means you get the direction of velocity. It gives the direction of velocity. At that instant, it gives the velocity vector plot. That means you can find out, for example, in a XY plot, if you have a streamline like this, then you tell the flow is only along the x direction. That means this gives the direction of the velocity, the flow direction. Next is that there is a term known as stream function, which will be taught by Professor Suman Chakraborty. A streamline is specified by a stream constant stream function, psi. The stream function will be defined by Professor Suman Chakraborty, and he will show from the equation of the streamline. For example, the equation of streamline is dy dx in 2 dimension, for example, v by u. In 2-dimensional, the equation of streamline is v by u. Okay, just a minute. Where are the papers? Hey, Subrata. The equation of streamline is v by u. Okay. Equation of streamline is dy dx is v by u. For example, for our understanding simple, u dy minus v dx is 0. By taking this into consideration for a 2-dimensional flow, he will show you that there is a definition of stream function, which is defined as this way. U is equal to del psi del y, and v is equal to minus del psi del x. And you will see that the stream function, streamlines are specified by constant stream function. If streamlines are spaced very close to each other, that means the stream function variation is very sharp. You understand, the gradient is very sharp. This shows that there is more flow. The fluid is flowing with high velocity. So you get a magnitude of the flow velocity if we know this stream function spacing. By one streamline spacing, streamline, we cannot have the magnitude of the velocity. If we have a series of streamlines, we can find out an idea of the direction of the flow, and by their close spacing and the corresponding stream functions, we can find out what is the flow rate taking place. Okay, all these things I cannot cover in one lecture this way, because you have to see this from the book. Any other question, please? I will be very happy to answer. Because until and unless this is clear, there is no point of giving more material.
Sir,
Excuse me, sir.
here is the unsteady flow means the turbulence is there, na?
No, not the turbulence. Okay, I tell you. Just a minute. Unsteady flow, let me define. Please wait. I think it is better for me to clarify your queries rather than a unsteady flow is defined where the flow parameter, for example, the flow velocity, all flow parameters are independent of time. Try to understand. Independent of time, first line of definition. Now, turbulent flow is a flow which is inherently unsteady. Forget turbulence. Turbulence is very tough thing. Till today, people do not understand much about turbulence. Inherently, the unsteadiness is prevailing in all flow. Small fluctuations will be there. Turbulent flow is inherently unsteady. Don't mix up with the jargon. You rather think this way, that inherently fluctuations or unsteadiness is there in all flow fields. But still we tell the flow to be steady, that if we find that if with that fluctuation, the mean velocity or the mean value of the parameter does not change with the time. Time means what time? Time of investigation. That means the fluctuations time scale should be very small as compared to the time scale of investigation, physical time scale. Then the mean value may remain constant with time if the flow is steady. So steady flow is defined in that way. But if the mean value changes with time, then that flow is unsteady. So any inherent unsteadiness may not make the flow unsteady. That's why with reference to your turbulent flow, I tell you, turbulent flow means wherever there is random fluctuations in the flow velocities. But a steady turbulent flow is there. Unsteady turbulent flow is there. In a steady turbulent flow, the mean velocity, that means the mean, that if you take a mean with respect to the time, the fluctuations go out. That means this does not vary with the time scale of investigation. So that is known as steady flow. Okay, I am telling that mean will be varying when the flow will be unsteady. You unnecessarily don't mix up this issue with the understanding of, so see, there are various ways by which the mean will vary. But in a steady flow, the mean will remain constant. Don't consider this as inherent fluctuations that there are not. There may be number of inherent fluctuations. But for a single parameter, try to understand. If a single parameter velocity, if the mean velocity, if over a fluctuation, there is a fluctuation of velocity, but fluctuation is so small and so rapid that over a certain time interval, which time is very small compared to our physical time scale, this goes down. You understand? We define a mean which is constant. That means over that time scale again and again, if you make the mean, that remains constant with the time. Then we call the flow is steady. But that may also change with time. That is the unsteady flow. Yes, very correct. That way the flow, yes. So my definition of steady, unsteady may be appended with one statement. If you write that, it will be extinguishing all your queries, that if we consider any flow or any system is inherently unsteady, then we have to define steady flow or steady situation in that way. This inherent unsteadiness which causes the fluctuations of some parameter, any parameter, in such a way that the time scale of fluctuation is so small and the fluctuations are so rapid, so that the mean value, any mean of any parameter over a time scale is constant. This happens when the time scale, if you make, is comparable to the time scale of our physical problem. You understand? Stream function I am not telling now. Don't ask, because this is the problem. Actually, I am telling you, you don't tell your students or encourage students to ask anything, because this way many jargons, many information hinders our understanding and the concept. You make this base, then we will go to stream function definition. Stream function is entirely different. I am not going to discuss this because Professor Suman Chakraborty will discuss this stream function. Stream function is the consequence of continuity. Stream function is defined as a consequence of continuity, and it will be shown that stream function is constant along a streamline. Stream function concept is different. This will come afterward. This is a consequence of continuity. So until and unless continuity equation, continuity is conservation of mass. So don't unnecessarily confuse. Step by step, we learn stream function, then we will see as a corollary of this definition, stream function remains constant along a streamline. So therefore, you can specify a streamline by a given stream function. So far we know streamline at any instant of time. To specify a streamline, a map of streamlines, a family of streamlines, what you have to specify at instant of time. At this instant of time, this is the streamlines of a flow field. And this gives only the information about the direction of the velocity, nothing else. But you will see after reading the stream function, if this is closely spaced, it gives that the velocity is more, flow is more. If I tell you, this will be mere an information. Where is your concept? You can ask me, sir, how do you tell? I cannot explain until and unless I define this stream function. But this is as an information that a series of streamlines are given to you. You can say, oh, the flow velocity is taking. For example, parallel lines, parallel to the abscissa. If abscissa is your x-axis, oh, flow is taking place along x-axis direction. The flow along x direction. Oh, streamlines are so widened, that means it's very little flow rate or very little flow velocity. These are the qualitative information that is brought. But if stream functions are specified, psi, it is given, is equal to this, is equal to this. From that and your scale length, you can find out quantitatively what is the flow rate. That means the flow across two, flow along two streamlines, across two streamlines, along these streamlines, across two streamlines. But only from this knowledge which I have told, you cannot get all those. Clear? Okay. Now, time is there. There is absolutely no time, but I like this. Any question, I think it will be much better that if we interact this way. Now, let me little quickly finish this one, that let me take another 15-20 minutes, but I just request you, all of you, that if you have any query, please ask me when I teach. It will be better, that otherwise what will happen, that said this slide, that slide, it is difficult for me. So immediately you tell me, sir, what you have told I cannot follow. Now I will tell you three very important things very hurriedly, that translation, please, these three are very important. I told you at the beginning that it is the consequence of kinematics, that is the motion, description of motion, and there is a continuous motion, the concept of velocity comes. So the velocity that gives rise to these three very important characteristic features, that translation, deformation and rotation. And this word deformation distinguishes fluid from the solid, as I told in the first class yesterday. Now what is translation? Translation means simply a fluid is translating. That means, let me explain. Consider a flow field Eulerian version, where u component of velocity, u, y component v, w, all are constant. That is totally uniform flow. So u, v, w all are constant, and consider for our understanding a simplicity that steady state, steady flow. That means nothing is changing. That means a flow field where u is constant throughout, neither varies with x, nor with y, nor with z, v constant, w constant. Then what happens if you identify a fluid element that simply translates, continuously translates? Because there is no scope of any change in its dimension. Why? Because if you consider this rectangular parallelepiped fluid element, if you consider this edge, all the points are moving with the same velocity. So therefore there is no question of extension of this linear element. Similarly, if these all points move with the same y velocity, so there is no question of any rotation. That means there is no question of relative displacement of any particle in y direction with respect to another particle. That means all lines remains unchanged by length and move parallel. So in three-dimensional way we can tell the all planes move parallelly without any change in the included angle. A rectangular parallelepiped remains rectangular parallelepiped of the same linear dimension. That means there is no change in the angle. No, a plane, it is just translated. It is neither distorted or not change in its linear dimension. This happens when all the flow velocities are constant. This is known as translation, which happens in a solid body. A solid body, when it pushed, it moves with the same velocity, the solid body motion. That's why we call it as a solid body motion. When it moves with the same velocity in all directions, this is known as translation. Sometimes I call it as pure translation, solid body translation. Okay. Now the most important thing is the deformation. Let us consider the deformation. Now deformation are of two types, linear deformation and angular deformation. Now what is linear deformation? What is linear deformation? One is linear, another is angular. Now for our understanding, simple understanding, let us consider a two-dimensional case, XY plane. Rather, this will be not good. I take another. Let us consider here XY plane. Let us consider in XY plane a case where u and v are the velocity component. U is a function of x only. Steady flow. First of all, I tell you the flow is steady. And v is a function of y only. Let a condition like that. That means u is the x component of velocity and it is a function of that coordinate. That the velocity is a function of the coordinate along which it is defined. U is not a function of y. And v is a function of y, not a function of x. Then what happens if we have a element like this, A, B, C, D. In a two-dimensional plane, a rectangular element like this whose length is delta x and this is delta y. Now, if this is so, what happens? Let us first recognize that each and every particle on AB will not move with the same u velocity in this direction because u is a function of x. And if in the sense of coordinate direction positive, we consider that u increases with x, that means del u del x is positive, then what will happen? This B has an opportunity to have higher velocities than A. That means each and every particle along AB will move with higher velocity compared to the particle before it, which will make an elongation of AB. Now, since V is a function of y, not a function of x, then all these particles will move with the same V velocity. That means this line will be displaced parallelly on the y direction. That means there will not be a relative displacement of B in y direction with respect to A. Both of them will have the same y displacement because V is not a function of x. It is only function of y. So therefore, AB will be elongated but will be displaced parallelly in the y direction. Similar is the case of y. Since V is a function of y, so all the points along AD will be having different displacement or rate of displacement in the y direction, which will make this linear element to be elongated. Whereas the u component is not a function of y. That means all the particles here has got the same u component, which means this line will shift or move in the x direction parallelly. There will be no relative displacement of D or any other particle with respect to A. Clear? If this is the concept, then we can write the new position like this, where the included angle remains same because they are moving parallelly, and this becomes our new position B dash, C dash, D dash. Now you see, after a time delta t, this has moved with the elongation. How the elongation takes place? With this concept. Now let me write mathematically this concept. This I have understood, but I have to write mathematically. That means A has moved a distance u delta t, whereas B has moved a distance which is what? U plus del u del x delta t. Okay? So this is the movement. Oh, this will be the pair. U plus del u del x into del x delta t, because this is moving with this velocity, u plus del u del x, and after a time delta t, this is the displacement. So this is displacement of this. So now if we want to find out this displacement, this length AB, this is delta x. What will be this length? This length will be this minus this one. So what will be this one? This one is u plus del u del x delta x into delta t, this one, plus del x, that means pull this, minus u delta t. That means this will be del x plus del u del x del x. This will be cancelled, u delta t del x into delta t. So this length therefore will be, if I take delta x as common, 1 plus del u del x delta t. Clear? That means this is the elongated length. So similarly, with this concept, the elongated length will be there like this, that if this is the displacement, the A will be displaced vertically by, here if we define the velocity v, so v delta t. since v is a function of y, so this displacement, that means d to d displacement, because d will be moving with a velocity v plus del v del y, because this is the change in velocity of y component velocity for a change of del y, for a change of length of del y. So this velocity here, y component velocity is not v plus del v del y, and del v del y is positive. So therefore, v changes with y and del v del y is positive, this will be elongated. That means this will be v plus del v del y into delta t. And in the similar way, we can find out that this, like this length will be, this length here I am writing delta y, just like delta t, 1 plus del v del y into delta t. So therefore, this is the elongation in the length. Okay. So this gives you the concept that if the velocity is a function of the space coordinates along which it is defined, there is no change in the included angle. The sides are changing parallelly. Okay, but they get elongated along their own directions. That means a delta x element gets elongated to this and delta y element gets elongated to this. And this gives you the concept of linear deformation. Now, I show you, what is this? I show you this. Oh, where is this? Figure. Can you find out, Sukumar? That figure, I will show you a three-dimensional figure which may be difficult. I could have kept it. Wait. It is there. See, in a three-dimensional figure, it looks like this. So this is the elongated length in the x direction. This is the elongated length. So ultimately what happened in three-dimensional figure, when u is a function of x only, v is a function of its own coordinate, and z component of velocity is a function of its own coordinate, then it will be translated in such a way that the planes will move parallelly. So there will be no change in the included angle, but the dimensions, this we map the initial one, so dimensions are changed. So they suffer a linear dimension. Now, if we define now the linear rate of change of linear dimension in x direction, limit of this delta t tends to 0 as the rate, strain rate, that is the rate of elongation of x, rate of elongation per unit length, rate of elongation, I am sorry. So elongation, so first of all, elongation in x direction, or in x dimension or x direction is what? This minus del x, that means del x into, or rather del u del t, del u del x into del x del. So this is the elongation in the x direction, this minus del x. So rate of elongation in x direction, rate of elongation in x direction, can be written as, this is expressed as epsilon dot xx is the change in the elongation per original length per unit time, that becomes is equal to del u del x, because that is defined as change in the elongation per unit length. So del x will be cancelled per unit time. This is the elongation in x direction. So rate of elongation in x direction is the elongation per unit length per unit time. So if you write that then this will be divided by delta x and delta t and will finally give this. And this is given by sometimes two subscripts. This is because of this, or sometimes we give one subscript also, epsilon dot x. But two subscripts are usually given. This is because of the fact this one subscript says that it is in the plane x, because x direction elongation in the x plane means the plane which is for which normal is x direction, outward normal, x and minus x direction. But this is elongated in the positive x direction. If you consider this elongation, this will be in the negative x direction. So in both cases it is the plane and the direction. Both indices are given epsilon dot xx as del u del x. In the similar way, we can write that, the elongation in the y direction, rate of elongation or rate of elongation in x direction, rate of elongation in y direction as del v del y, and rate of elongation in z direction as, and this is defined as the linear strain rate. Linear strain rate. That means rate of elongation rather per unit original length. Per unit original length. Rate of elongation per unit original length in x direction is this. Rate of elongation per unit original length, that means you divided it by delta y. That means this is this one. Okay, 1 minus del v del y. Oh God. Del v del y into delta t. So if you minus delta y, then you get this one divided by delta y and delta t. You get del v del y. Similarly in z direction also, this minus delta z, this will be cancelled. Del w del z delta t del z divided by delta t del z will give you del w del z. Sorry, del w del z. That means this is defined as linear strain rate. So linear strain rate in x direction is what? The rate of elongation in x direction per unit original length, that is del u del x. Rate of elongation in y direction per unit original length is del v del y. Rate of elongation in z direction per unit original length is del w del z. So these are defined as the strain rate. Now let us work out one thing, that because of this linear extension or linear elongation, we have a change in the volume. Initial volume v cut, I have told that we use this because to discriminate it from the velocity v. So this is del x del y del z. Now the final volume, if we consider the change as del v, so final volume will be v plus del v, which is the elongated length here, del x into this one, 1 plus del u del x into delta t into the y dimension 1 plus del v del y into delta t and delta z 1 plus del w del z into delta. So this we are using these dimensions. That means these are the change dimensions. So now if we define the volumetric strain rate, or the change in volume, rate of change in volume per unit original volume. Rate of change in volume per unit original volume. That means what is rate of change in volume? Delta V is equal to this. If you neglect the higher order terms, if you just multiply and neglect the higher order term, I first write rate of volumetric change is rate of change in volume per original volume per unit time. Now what is the change in volume? This minus del x del y del z, And if you neglect the product of this into this, this into this, this into this higher order terms product, which creates delta T square, because these are infinite small quantities, then the change in the volume you get delta V as del U, delta V as del U del X plus del V del Y plus del W del Z into del X del Y del Z del T. Now this is the original volume. So delta V by the original volume divided by the delta T becomes is equal to del U del X plus del V del Y plus del W del Z. That means this can be expressed in terms of the linear strain rate YY plus ZZ. Linear strain rates epsilon XX, epsilon YY, epsilon ZZ, sum of the linear strain rate. And it can be told that if the volumetric, that now in an incompressible flow, as I defined yesterday, is a flow where the change in volume is 0. Then change in volume is 0 means what? It does not mean, one very simple case, trivial case is no linear dimension is changing or elongated. But they may be elongated in a sense that they counter, one elongated, another shortened, so that the total volume remains same. So that condition to be satisfied, the sum of the strain rates, will be, linear strain rates will be 0, which other way relate. Now my main intention is to define the strain rates, find out the elongation, and finally express these strain rates in terms of the velocity component. So therefore, strain rates are related to the velocity gradient. Epsilon dot xx, linear strain rate in x direction, is the velocity gradient of x component with x. So del V del Y plus del W del Z. So therefore, the sum of these three linear strain rates is equal to sum of these three velocity gradient, del U del X, del V del Y, del W del Z. And this is written, if the velocity vector is this, as I have told earlier, vector notation, this can be written, this part can be written as divergence of the velocity vector. Del dot, del is a operator, I del del X plus J, this is simple vector calculus at school level, del del Z. So the scalar product, this is known as divergence, del dot V. So therefore, divergence of the velocity vector equals to the sum of the three linear strain rates, which equals to the volumetric strain rate, which becomes 0 for an incompressible flow. Now I like to know, because of many questions and answering questions, I did not get time. What is my time left? 10 minutes. Okay. Within 10 minutes, I will just finish the deformation, that sense. What is now? Let us consider now a situation. Now this is linear deformation. Now let us situation where u is a function of xy. So far we did not consider the variation of u with y and variation of v with x. We consider this situation, x component of velocity varies only with x, y component of velocity varied only with y. Now in a most general sense we consider u is a function of both xy, v is a function of both xy. Then what happens? Then along with this elongation, now what happened? When v is a function of x, that means each and every particle here moves with different y component of velocity, because of the fact that v is a function of x. It is not only the function of y. So therefore, this point has got an opportunity to have a relative displacement over this point after any interval of time. So therefore, at any interval of time of delta t, if I map this AB, it will not only elongate by its length or by its x displacement, but it will go like this. That means this point has a relative y displacement than A. Other things are routine mathematics. I don't want to do that. You just follow it. It is given in any book, in my book also. So therefore, there is a chance that this line gets mapped like this. Similarly, so therefore this line is not displaced parallelly as it happened when v was not a function of x. Similar is the situation here, that points on this line AD has different u component of velocity. Why? Because u now is not only a function of x but also a function of y. That means a particle d, for example, this particle has an opportunity to have a relative x displacement in this direction as compared to a or relative to a after any time interval, so that this line moves heels in this direction. It cannot move parallel along with its elongation because of the variation of v with y. So therefore, along with the linear extension, these two linear elements which was initially perpendicular to each other ceases to be perpendicular. There is an angular displacement. This is given as delta alpha and this is given as delta beta. Okay. Now if we find out this value of delta alpha here, we will found tan delta alpha. Since delta alpha is very small, we consider an infinite small time. That is the technique of calculations of mathematically, so that I can define the parameter at a point. So delta alpha, tan delta alpha is delta alpha. Okay. So this becomes is equal to, what is this quantity? Del v del x del x, del v del x del x divided by into delta t divided by del x into 1 plus del u del x delta t. Where from I get this? This I get from the displacement. This is already known, that u plus u delta x into 1 plus del u del x delta t. But this thing is what? That you get from here. This is displaced by an amount v delta t. This point is displaced by an amount v delta t. Here the value is v. But here the value is what? Here the value is v plus del v del x. V plus del v del x del x. So therefore, this one. There the v is that, this value is that v plus del v del x. The value of y component velocity b at b is v plus del v del x, change with x del x into delta t, neglecting the higher order component. So therefore, for a time delta t, so this will be, this is the value of y component of velocity times delta t. So this will be the displacement. So if you deduct this part, the relative displacement with respect to this point will be del v del x del x del t. That is so simple, you can just make it. There is no point of that I will do these things to you line by line. So that means this is simply that this point has a velocity v, this point has a different velocity given by v plus del v del x del x by virtue of the fact v being function of x also. So therefore, this is the displacement, and if you solve this neglecting this, now if you do that, now you let limit delta alpha delta t, okay, is equal to at delta t tends to 0 becomes is equal to del v del x. This cancel out, and if you take that and limit delta t 0, all terms are cancelled, delta t by delta t. So if you expand this 1 plus del u del x delta t, so all terms containing delta t and higher order, so it will be only del v del x. Similar way, if you calculate this thing, I am not spending time, time is short, tan delta beta is delta beta will be this divided by this. You see this quantity is del u del y delta t, and this quantity is del y. Already I have done this 1 plus del v del y delta t. You will get this thing as del u del y. And sorry, tan beta is, I am extremely sorry, tan beta is this divided by this. Time is very short, that's why I am in a hurry, that this again I have to write. Tan beta is actually del u del y delta t divided by del y 1 plus del v del y delta t. So this is tan beta, and again if we take this like this, that limit of delta beta delta t at delta t tends to 0 is equal to, what is that? Del u del y. Now, one thing. Now we define something. This is our mathematics test from the angular deformation. Now you see, we define one thing, that because of this deformation, the original angle 90 degree is now changed to this angle. So what is the change in angle? Change in angle is delta alpha plus delta beta. This is the change in angle. Now the rate of change in angle is delta alpha plus delta beta divided by delta t. Clear? So rate of change in angle is delta alpha plus delta beta by delta t at limit delta t tends to 0. And this is given by del v del x plus del u del y. This is the rate of change of angle for this element. The rate of change of angle is delta alpha plus delta beta by delta t, limit of that delta t tends to 0, which becomes del v del x, and this is defined as rate of angular deformation. I am not writing. This is known as, should I write, rate of angular deformation. And this, you see, the rate of angular deformation takes the two subscript. This is in xy plane. This is given by xy. It is del v del x. Sometimes it is denoted by term gamma dot or epsilon dot xy. That means this is in xy plane. This is related to the angular deformation of linear element in x direction and linear element in y direction. This is sometimes known as shear rate. Shear rate in xy plane, and this originates from the angular deformation of linear elements of x and y, which were originally perpendicular, but their angle is distorted. That is known as angular rate of angular deformation, and that happens because of this typical variation of the velocity component, x component with y and y component with x. This is only the concept. Now we can find out in other directions also. That means if you have a rectangular Cartesian coordinate system like that, it is in the xy plane, but we may have this thing in the xz plane, yz plane, and accordingly you can write that. That is there in the book. I am not going to write that, but just I will finish by telling another concept that is associated with this deformation. Since the angular deformation is this, then another concept I will tell with this deformation is this. Related to this deformation, another concept comes like this. This type of deformation, that means this has an opportunity of more y displacement with respect to this, and this makes a deformation of the change in the angle, but at the same time this brings a type of rotation. When this line becomes like that with respect to that, that means we can conceive it as if this linear element rotates about this point. Similarly, this linear element rotates about this point, but this rotation is in opposite direction. Now, if I define the angular velocity as our concept, basic concept of the angular velocity, the rate of change of angle with respect to time, that means the angular velocity of the linear element AB is delta alpha delta t, limit delta t tends to 0. This is the angular velocity, which is nothing but del v del x. Similarly, angular velocity for the element AD, delta t, limit delta t 0 is del u del y. That means I can argue that del v del x gives a sort of angular velocity for the element AB, and del u del y gives a sort of angular velocity of the element AD, but they are in opposite directions. So they are of different sign. Now we define in fluid flow a rotation. The rotation is defined at a point. So if rotation is defined at a point A and about an axis, these two linear elements are rotating about the z axis. So therefore, if we define the rotation at point A about z axis by its definition as the arithmetic average of the angular velocity of the two linear elements which met at that point and were initially mutually perpendicular, then by definition it is half of these two but with the opposite sign, because they are of different direct rotation. By convention, if I take the anti-clockwise as the positive one, so I get del V del x first with the positive sign minus del U del y. This is the sign of, this is the concept of rotation, and this rotation requires a variable about the z axis, or sometimes we write xy half. But one thing is clear here, that if we follow the index notation, then you see that this index notation, this is symmetric. This, where is that? Stress, this rate of strain tensor, but this is not symmetric, this is anti-symmetric, because omega xy is not omega yx. Gamma dot xy, or you can write epsilon dot xy, is gamma dot yx, or whatever, right? This is the same, these two things are same thing. This is symmetric, but this is q symmetric, that means omega xy. This you can write dot, because it is the velocity. Velocity means rate of change with time, so dot, so minus omega dot yx. Now this is also there in different other coordinate systems, x, y, z, is other plane, that means there is omega dot yz, there is omega dot xz. Okay, so omega dot yz and omega dot xz are there, this can be defined, and we can define the omega dot as, now if I write this component, that you can find out in the similar way the rotation and deformation at different other coordinate system, but I just write to you, please, time is over. Oh God. Then okay, you see my book, because I don't want to write, because this can be written at different, and if you write the components, especially this omega 1, omega ij, or omega xy, omega yz, sometimes omega xy, I think I write this way, that is better. It is with respect to x axis and it is with respect to y axis. Then you will see that this can also be expressed by their expression in a vector form. In a vector form, we can express this without the two surfaces, only by one surfaces. That means physically implying that it is about a axis, then in a vector form, which is nothing but curl of the velocity vector. Curl means what? This is the vector operator delta, the cross product. This vector operator I already told, this is like this is a simple operator, this vector calculus at school level. So if this operator with the cross product, vector product with the velocity v, v is I u j v, and this, as you know from your elementary knowledge, so this can be written in a determinant form, this one, I j k are the, if you split it in terms of the scalar component, that means this will be I omega x plus j omega y plus k omega z, or w, whatever you call, then this is curl of that, that means del del x, del del y, del del z, and u v w. So this equals to this curl of, this is the here, this is the omega, and this quantity, that means twice this is the, this of this is known as vorticity. Vorticity is also can be expressed as vector, but it is not a vector, it is an q-symmetric tensor, whereas the shear rates are the symmetric tensors, components of the symmetric tensors, as the components of the symmetric stress tensors are the shear stress. And Professor Suman Chakraborty will tell you that shear stress are proportional to the shear rate for a class of fluids known as Newtonian fluid. Now next, just before I conclude, I tell you two special cases. Now you know that gamma dot or epsilon dot xy is del v del x plus del u del y, and omega dot xy is omega dot z is half del v del x minus del u del y. Then mathematically, immediate a query comes when del v del x is equal to minus del u del y. Then what happened? That gamma dot xy is 0 and omega dot xy is del v del x or del u del y. What is this situation? This situation is like this. Quick. This situation is like this. Just for your understanding only, I am doing this. This situation is like this. Now, when this is minus of this means that if this is plus, so this del v del x del t, and it is del u del y del t. Now, minus sign means if this has a, in the positive sense, as a more velocity AB with x, then this will be less velocity. That means u minus del u del y. That means this u is less as compared to this u, which means that this point will not have a relative displacement in this direction with respect to rather in the opposite direction. That's why the negative sign is there. That means you will have to conceive like that. And when these two are same, delta alpha and delta beta will same. That means the included angle will still remain 90 degree. And that is the case where there is no deformation. That's why by mathematics also this becomes 0. That means this is a special case when del v del x is equal to minus del u del y. Then there is no angular deformation, and you see from the picture the particle rotates as a solid body rotation without any change in the included angle. And another case is there when del v del x is equal to del u del y. In that case, rotation is 0, z is 0. But what is there? Gamma dot xy is either 2 del v del x or is equal to 2 del u del y. How we conceive this case? This case is conceived this way. Here both are positive. If one is positive, another is also positive. So this you can conceive this way. That means this delta alpha and this delta beta are same, but they are in opposite direction. So that's why, because of the velocities are given the direction, angular velocity, one is positive, another is negative. So this is moving with the same velocity, so net result is 0. By definition, rotation is the arithmetic average of the angular velocities. But there is a solid deformation, net deformation, which is twice del v del x del u del y. This is all about translation, deformation and rotation.
Sir,
I am sorry I am late. I didn't want to
excuse me,
continue, but
one question, sir.
questions afterwards, please. You let Professor Suman Chakraborty start, because I suffered because of, I did not suffer. I told that, okay, it is good that we go on discussing. I think it is better let Suman Chakraborty take over. In our tutorial sessions, we will entertain the question. Okay, I declare it tutorial session. There is no need of solving many problems. One problem, two problems we will solve. I was very happy in today's discussion section, for which I am late.